So I'm Aleksey, and I talk about benchmarks as usual. Let me have a few preparation steps here. Okay. Right, so benchmarking, what could be easier, right? Just 2 timestamps. So everything I will tell you is a lie. Well, with benchmarks, it's double so. So think for yourselves. As the warm-up, the real stuff which was there on InfoQ in the article, which was called How to Approach the Performance Engineering. So how much for instantiating a string, and this is a real code. Any problems with these benchmarks? That's the opinionated problem, right? But anyway, in this test, there is a major problem. I have to at least divide by the time difference by 1,000 to actually answer the question, how much for instantiating a string? So before looking for the complex answers, looks for a simple one, right? So this benchmark is incorrect because the metric is incorrect there. Right. So to the theory, I did a lot of benchmarks, and I've written a lot of benchmarks, and I understand that people usually do benchmarks for 4 reasons. The first reason is for Holywar, whatever, for good or for bad, for marketing, for engineering, and for science, and we will dive into this a little bit. So in the name of Holywar, my favorite example is computer language benchmark game. The real intent of that project is not to facilitate Holywars, but it's so useful in them because you have numbers in which you can just take and post into the forum post and say, how can you not believe that my language X is faster than your inferior language Y? Can't you see the numbers are better there? Well, this is a very questionable approach. Many comparisons in these projects are hardly fair. For instance, they are comparing statically compiled versus dynamically compiled languages in the same use cases. We don't really know what exactly the benchmarks there measure. My favorite test p-digits there, if you look at the top 10 implementations there, the second top implementation is Lua, surprisingly. Well, and it's not really surprising if you look at the code, because all the top contendants there are delegating the task of calculating the first 10,000 digits of P to GNU GMP, which is written in C, and you only actually benchmark the FFI interface to that library. So it's not really a language benchmark per se, right? It's just a very tiny thing in your implementation, which is FFI. Marketing benchmarks, my favorite example are spec benchmarks. Nobody really cares how representative they are. We do care that they are born in this fury madness of Mountain Doom, where all vendors agree that this is the golden benchmarks and we should all align our marketing materials on the values that these benchmarks produce. And marketing benchmarks are useful to set marketing goals, to use in adverts and all that stuff. But we are engineers. We don't mostly care about that unless our management told us to care. In the name of engineering, if we can't measure something, we can optimize it. That means that if we want to optimize something, we need to set the system in some predictable state so we can quantify the improvements that we are about to do in that system. This benchmark usually focus on particular parts of the system. Rarely they do the complete end-to-end performance kind of investigations. And usually they have more resolutions than marketing benchmark. And in the name of science, when we want to generalize all the performance characteristics that we see and derive the sound performance model of our system, so we can predict how the system will perform in the future. So we can just keep calm and deploy in production then, right? This is the most horribly difficult, but the most reliable target for benchmarking. So we will, in this talk, we will only care about the latest 2 goals. We can talk about the first 2 as well, but those are not interesting for us sane guys. For the scientific approach, when you deal with benchmarks, you want to answer the question, how does the benchmark react on changing the external conditions? Because you want to figure out how the actual performance model that you derive from the empirical data matches the model that you have in your head about the system, the model that you use to predict how the system will perform in the future. And you will have lots of sub-questions when you will try to answer this one. So whether the results that you get from the benchmark make any sense at all, and whether this benchmark really reacts on the changes you wanted to react, and the vice versa in reverse. Engineering approach is somewhat simpler. It only asks itself, well, why doesn't my benchmark run faster? And that enables us to directly observe if our experimental setup is sane, whether the bottlenecks that we see in the benchmarks are in those parts of the systems that we want to optimize, because we want to isolate the particular problem or particular behavior of the system. So by analyzing what system actually spends time doing, we figure out whether our approach is sane or not. All right, shameless plug, GMH. It's there in OpenJDK. When used properly, it helps to mitigate VM quirks. We have support for JVM languages besides Java. So Scala folks use that for some of the comparisons. I do believe some other languages will also do. It also supports anything callable from Java, like Nashorn, which you can call through JavaX script engine, blah, blah. All right. And I will tell you two stories. I actually told these stories on internet already. So those of you who read actually my blog or my articles will be bored, I think. But I have cat pictures this time. So the first story is about the methodology implications when doing the benchmarks. And I have the complete story and narrative there in Nanotrusting Nanotime article. I didn't intend it to be that way, but people, when they read this paper, they tell me that this story was a deal breaker for them when they try to build out their own harness. When they read this article, they say, oh no, I don't want to deal with this at all. So I will let other guys deal with this. All right, so let's do some model experiment. It is the question which is remarkably frequently asked on Stack Overflow, as if Stack Overflow is representative. So what's the cost of volatile write? Right? It seems to be a very simple question. It's just, I don't know, the 7 words in this question. How hard could it be, right? Let's measure it. Let's measure it with GMH, right? So we have 2 fields, a plain field and a volatile field, and we increment the plain field and increment the volatile field, and we have the baseline to estimate the overheads for the harness itself. So we will measure it on some platform on my laptop. We will take this 2 nanoseconds, 3.5 nanoseconds, and 15 nanoseconds. And people looking at this data will say that it's evident that using volatile makes your application 4 times slower, which means if I use volatiles in my applications, it will get 4 times slower. So I should not use volatiles. Is this true? What? Yeah. What's the problem with this benchmark? Is there a problem with this benchmark? GMH actually handles all that. The fatal flaw there is writing volatiles is the heavyweight operation. And so if we do this kind of thing continuously, we drown the system in volatiles. And this is probably not the behavior that we expect from our production system. If we have this problem in production, we have major problem except for benchmarking, right? Already. So what do we really want to know? What is useful for us to know is what is the volatile cost in some realistic conditions? This is obviously not a realistic condition when all I do is doing volatile increments, right? So how do I do it with GMH? We need to basically back off a little bit before doing this heavyweight operation. In GMH, we have the API support. We have this major class black hole, which consumes all sorts of things, including CPU time. And it consumes CPU time, hopefully linearly to the number of tokens. So by doing this kind of thing and by juggling tokens, we can actually mix the heavyweight volatile operation and lightweight, presumably lightweight operation in consumed CPU. So now we have the experiment with 1 degree of freedom. We juggle the number of tokens, right? So we measure it. Oh, by the way, while we are at it, we have the baselines, right? And now we have backoff there, and we have three possible variants of baseline to contrast the cost of volatile increment. Which one of this baseline is actually correct? Which one we should compare against? We don't really know, so let's just measure it, right? So we have 5 tests, 3 baselines and 2 tests. This is what people will show me while running these tests, right? They will just show me some chart about like this and claim, okay, this is the performance data, go look at it. And I'm looking at it and see nothing there because it doesn't tell me just about anything. It's just, just the colored lines there. They will argue that there's the magenta line, which is barely above anything else, and so increment volatile is more costly, but I don't believe that because I don't really know if that difference is statistically significant at all, for instance, or is it just the systematic noise somewhere there. So we need to contrast this. The obvious thing to do this is to take a baseline and subtract the baseline from all the tests, right? So let's subtract baseline plane. Obviously, this red line is the baseline plane. It drops to 0. And the increment plane consistently costs me a nanosecond more, which is kind of expected for my mental performance model. And increment volatile has a tremendous cost when there is no backoff. But when I do significant backoff, the absolute cost of volatile ride compensates because my system has the time to recover from this heavyweight operation. But the collateral lesson in this, can we really subtract this baseline? Can we really subtract the baseline 0 from all this test? Can we? Well, we have 2 other baselines, so we can see how that goes, right? So we have baseline which returns 42. We add something that returns from that test, and our baseline starts to be faster than the tests themselves, even though we have the volatile rides and all this stuff there. People who are new to performance engineering are kind of say that this is some magic and I don't understand this, so I will go and develop some JavaScript instead. But we know this is the remarkable evidence that the performance is not usually composable. The performance of the entire system is not usually a linear combination of performances of each part of that system, which does something together. So if we have, baseline which does nothing, and the baseline is slower, and we have baseline which returns 42, and that code is faster, we have the third baseline which returns V, and it's still slower. So you cannot derive any knowledge from this, right? And so the lesson there is, since different baselines act differently because they are tests themselves. Every so often I come across the people who say, okay, we will measure this baseline test. Then we pick up the value of baseline, say this is some magic value, which is universally true because this is the universal constant we have just measured. And we will do this kind of arithmetic, including this baseline, as if it's some universal truth. No, baseline is just the test. With headlines like that, we can just count the plane as the baseline, right? And there we see, this is the simplistic model of volatile ride performance. When we back off a lot, it costs some small amount. If we don't back off and do only the volatile rides, it costs a lot. So luckily, we measured our basic test in the conditions on the left, where the difference is very, very bad. So this is what models are for. They allow us to explore the system behavior outside these randomly chosen configuration points. They allow us to predict the system behavior in future condition. They allow us to catch the experimental setup problems like we did with baselines just now. And moreover, these combinatorial experiments, when we mix different operations together, they allow us to reason about individual operation costs from their composite performance. Not derive is too much stronger word, but reason about it with some probability. And when I tell people this, they just say, well, there's nanotime, right? I can just measure stuff with nanotime. How hard could that be, right? So when you do benchmarks, you will do something like this. GMH does something like this. You have to measure time in some way. So if you have the workload, which is encapsulated in this work method, you have to make the timestamp before and after. Any problems with this approach? Well, system nanotime is not something, it's not something magical there, right? It's just a method which calls somewhere, which does something, and we really need to understand what is the performance implications of using nanotime. How do we figure this out? Yes, we benchmark nanotime. So in retrospect, in hindsight, you know that you have to care about two characteristics of nanotime. Latency, meaning the time to call nanotime. You can conveniently measure it with GMH like this by continuously calling it. Well, freaks like me will actually obsess and see if the generated code outside this method does not call system nanotime on each invocation, and it's not calling it that. We just call it in the loop and do the two major timestamps. And the other thing is granularity or resolution, meaning the maximum non-zero difference between two consecutive calls. You should normally do that by allocating the array and just polling system nanotime and then taking the minimum distance between those guys. But we can have a tricky busy loop which spins until we have the new value there. If our latency and granularity tests produce the more or less the same value, we can argue that the overhead of this spin loop is actually minimal. Right? So I did this test. It's actually very simple to run. So I put it on the internet and asked people to run it when I was running it on my lab servers as well. And this is the typical numbers that I got. This is Linux. This is the typical Linux picture. Regardless of client or server, the latency and granularity of nanotime is closer to 25 nanoseconds. Not that bad, not that good actually, but this is what you have. If you have the volatile write, which takes you 15 nanoseconds, you can't really measure it with the two system nanotime calls because you will drown into the granularity of this thing. Solaris is the same. The clock rates are a bit different on the machines, so the results are not directly comparable, but it's in the same ballpark. It's 30 nanoseconds, right? Now we go to the interesting operation systems, which our customers blindly run, like Windows, for instance. And their latency is actually very good. But the granularity is horrible. You can call system nanotime 26 times, and only the 27th call will return you the new value. So probably if you average across these differences, the central limit theorem will average you to the real value, but I would not count on that. And this result was on very large, well, that's actually Windows 7, so it's not very large. But we also had the Windows Enterprise Edition, which was running at very large machine with 32 hardware threads. And we can try to run this benchmark with the 32 measurement threads. This is what we have. So we have like 15 freaking microseconds to poll the time. And this is obviously a scalability bottleneck, right? Yeah?
Is the granularity benchmark affected by the fact that you're using a field?
No, not really. Well, I will take questions later, okay? Where was I? Oh, yes, and this is like wrong, right? It feels wrong to have this. But I told you already that this is not the right way to benchmark, right? We just drown the system in nanotime calls. This is probably not what production will do. So maybe we are running the benchmark in this edge condition, which nobody cares about anyway. So maybe it's not that bad. So we will try to figure out when it starts to, well, it used to say deteriorate, but this is the automatic spell check. And it seems fitting. So we back off before doing nanotime. But in this experiment, we have 2 degrees of freedom. We have back off, and we have the number of threads. So it gets tricky to visualize it, right? This is Linux. And you need to read this chart as follows. So the x-axis is the number of measurement threads. And the y-axis is the logarithmic scale, which measures the time to do system nanotime plus a backoff. So if system nanotime scales perfectly, we will have the performance line parallel to the x-axis, right? Because the time to do nanotime and backoff is the same. Yeah?
You don't really care about nanotimes time, you care that it's messing with your benchmark.
Yes.
So why don't you repeat whatever it is that you're testing enough times? So you know that nanotime is going to contribute the same amount, often the same amount to both your control and your experiment. Why don't you just make sure that you repeat your experiment enough time that, 15 microseconds at the beginning. Well, make sure the experiment runs for 5, 10 seconds, and make sure the control runs for 5, 10 seconds. And when you take the nanotime, it's going to be a small constant on top of both of those things. It's not going to make any difference. That you're thinking about the same.
No, I don't. So, yes, this experiment is actually running for minutes.
Yeah, also the point is just because it's constant with your control and your experiment, just subtract. So just say I don't, just it's a constant amount of time, I don't care. What I care about is the difference.
Yeah, you can't really subtract baselines, as I showed you already, right? All right. Can we keep questions before? Yeah. All right. So this is Linux, right? And we actually see that this nanotime is more or less scalable. There are some latency effects on the lower tiers when the nanotime cost is actually compared to the backoff costs, but it's all good there, right? And this is Windows. And I like to interpret this chart as follows. If we pick some particular backoff value, which will yield us, 10 to the 4th nanosecond per call, somewhere in the middle between 2 in third and 2 in fourth, right, the green line. So we do this kind of thing, right? We start to run the tests, and we start to bring more and more tests. And it all gets really cool and fuzzy and warm, and the performance stays the same until we hit some critical point at which our execution time starts to drag upwards. This is when we hit the scalability of nanotime itself. And the line which encompasses this thing is the scalability front for nanotime. Everything below it is the forbidden zone. You cannot measure anything there. So if you realistically try to measure the individual events on Windows and you don't know how many threads are there on the system or something like that, you have to put your experiment somewhere where the red line is, right? And that means you can only do in the ballpark of 20,000 calls to nanotime per second, which is not that much at all. So if you're running the application performance management system, which profiles your production system, running on the Windows platform for some freaky reason, beware. And I don't know why Windows particularly does that, because Windows is kind of closed box when I cannot see in there. But I can look into the Solaris, which exhibits roughly the same behavior, but orders of magnitude better. And this is really the payment for monotonicity, because users expect that the values that they get from nanotime are monotonically increasing. If we ever present the users with the retrograde time, their algorithms usually break badly, deadlocking JVMs, for instance, or something like that. And Solaris has the kernel call, which, well, not kernel call, but API call, which gets you the monotonic time. But at some versions of Solaris kernel, there were bugs which provided you with the retrograde time. So to make our customers not exploding their JVMs and products, we have to plug the leak on the JVM level by setting the static global atomic, which will record the latest observed time in this JVM. And we compare and swap it at each and every system nanotime call. Thus, this scalability hit. We're just paying for monotonicity for this. And it's remarkable. My laptop has I think, 7 clocks, and none of those are good enough for me. All right, so we have the Mac OS, remarkably the very frequently used by developers, and the latency there is also well, but granularity is bad because we use the microsecond precision call there. This microsecond precision call is actually guaranteed to be monotonic. There is another call which has nanosecond precision, but there is no place in the spec when it says any guarantees about its monotonicity. So if we switch there, and we are switching there, we will have to do this sort of trap with the atomic to prevent users of observing the retrograde time, right? So this is an interesting dilemma, whether you present users with the inaccurate call or with some accurate call with the scalability bottlenecks there. So we can just switch to nanotime precision call and pray to all gods that Apple would not have Mac Pros with 32 hardware threads anytime soon. All right, so the point here is that system nanotime is the new string intern, as far as I'm concerned. So giving the users the unlimited access to nanotime is like giving them the loaded gun. It may and should be used in the selected cases when you realize all the disadvantages like this. If you, for instance, maintain the benchmarking framework or some performance management solution there. And another lesson from there is that with the latency and granularity, things like that, most frequently the direct timing measurement is not available. And you have to derive your models from this collateral evidence by doing these large operations and doing this sort of math there. When I tell people that, they tell me this, basically. They tell me, whatever. You told us about nano and micro benchmarks. Our code blocks, which we measure with nanotime, are big enough, so our granularity and latency things are not really applicable to us, right? There's a pitchfork for them as well. And it implicitly answers the question which I got a lot. So if you, for instance, have the benchmark which has clear stages, clear setup stage and clear work stage, and you only want to measure the work stage, right? So how do you do that? Well, you do something like this. You have the loop, and you have the setup method, which does the work, which does the setup, and work, which we want to measure. So we want to skip setup. How do we do this? Well, obviously something like that. We just measure it with nanotime, right? Work can be decently heavy, so we wouldn't have the latency problem there. Is there a problem with this approach? You stay silent. So if we measure these things, right, we measure this guy which does the 2 global timestamps, right, before and after the loop, and this guy who accumulates the nanotime. And we run it with a different number of threads. This is what we will get. Blue line is the timestamps before and after, and the red line is when we doing the sum over per iteration timestamps. And the black line there is the number of CPUs on my systems. And this is throughput. So we measure it past the system capacity, and throughput just grows and grows and grows. Why? Hint, hint. So we can have the long running events which are happening outside our timing measurement, and we derive throughput from time. So if you underestimate the time, we have overestimated the throughput. So basically, this is what happens. If we have a thread which has this green work method which takes 10 milliseconds, and we have a setup phase which takes 5 milliseconds, and we measure only this green part, that each thread believes that it does 10 milliseconds per operation on average, and so it believes its individual throughput is 100 operations per second, and so we have 2 threads, so the throughput is 200 operations per second. This is what most people do. The problem, of course, comes when other 2 thread comes out, and they start to deschedule the first two threads. Each thread still believes its individual throughput is 100 operations per second, because that's what I measure with individual timestamps. But now I have 4 threads, and so the composite throughput is 400 operations per second. And I can show 1,000,000 threads there, and my perceived throughput would be 1,000,000 times faster, which is obviously wrong, right? So the lesson for this is that the timers keep the beats, and they can grossly over and underestimate the measured durations. And every performance metric that we have that depends on time, whether it's latency or throughput, is at fault. It's very easy to blow out on overloaded systems because we can have these unaccounted events in the thread lifecycle. It's very easy to blow up when your measurers coordinate with workload, meaning they are waiting, submitting the another chunk of work until the previous chunk of work returns. Gil has a very nice multi-series rant about this called coordinated omission. So go read Gil for this. Okay? It's bad. Another thing, when people start to do benchmarks, the very first thing they try to benchmark is freaking Fibonacci generator. There is no cases in my experience when I needed the Fibonacci generator in production, ever. Why do I need to benchmark this stuff? Well, it's arguably simple to write, but do I really need to do this? Well, is there a problem with this benchmark? Well, yeah. Well, garbage is the Java's problem, so yeah, well. Anyone? And our Fibonacci is growing very fast, and every single invocation of next, we have big integer add, which adds larger and larger and larger big integers. So this benchmark does not have steady state. And indeed, if we try to time each next call, we will see something like this. X-axis is the number of call, is the call number in the sequence, and the y-axis is the microseconds per call. So we can see it's linearly growing because our big integers are getting better and larger and larger and larger, right? And so if you do time-based benchmark, which runs for the given amount of time, the longer we run, the slower the benchmark appears because it gets slower over time. In fact, if I do this kind of experiments, when I run this benchmark with 1, 2, 4, or 8 seconds, the throughput, sorry, it's not throughput, it's average time. That's microseconds per op. It gets slower and slower and slower. And when you don't have steady state, you are faced with the 2 bad options. First bad option is do the time-based benchmark, meaning run for the desired amount of time. In what conditions would you measure this benchmark? God only knows, right? You would be very happy if your performance grows linearly with the invocation count, so you can probably derive something from that assumption. How do you compare 2 implementations which has unknown performance profiles over time is beyond me. You can do work-based benchmarks. Say you can run Fibonacci for 5,000 times in a row and measure how much time it takes, but you will face these timers, latency and granularity issues there, because probably what you will measure would be thin enough. You will see problems with emissions, and you will include lots of transients in your benchmarks. Transients like JIT compilation or any sorts of adaptations that you have right after you started to execute your next stride of work. Right? So it's really bad. Doing non-steady state benchmark is really hard. And except for the cases when you have to face this, for instance, when you do warm-up measurements or you want to measure the transients in your system, it is not a good idea to do non-steady benchmarks at all. Really, the only winning move there is not to play at all. You cannot usually derive anything useful from that data. There's the palliative relief for that. We can probably dodge the timer's latency and granularity caused by measuring in batches when we just call the method a number of times and only do the timestamps every once in a while. That will probably dodge this granularity and latency stuff, but it will still include omission and transients there. So don't do that. Fibonacci is the good example for your functional side of things, not for performance one. Forget about Fibonacci. That's the, if that's the only takeaway you get from this. Okay. And in the remaining time, I will cover the engineering approach. Those was more or less scientific, right? When we wanted to derive the model, or we want to understand how particular pieces of that model perform, so we can reason about the system as whole. And this is hard, right? I spent half an hour talking about this. Engineering should be faster, and it will be faster. You really want your results to be comparable. Right? You want your performance measurements to be fair. If you can read the caption there, it says, Professor Zapinski proved that the squid is more intelligent than a house cat when posed with puzzles under similar conditions. Obviously. So you want your results to be comparable. And to do that comparable or fair, you have to control little details. Every single tiny uncontrolled detail is the free variable, which probably invalidates your comparison. And libraries are the large complexes of these tiny details. There are lots of tiny details. Language runtimes are the huge galaxies of these details. Nobody would probably even enumerate all these quirks that runtimes could have, right? So this is the story. This is a weird story of Scala versus Java comparison, which was born on Stack Overflow when people were born to believe that the tail recursion optimization is the best thing that happened in computer science since the sliced bread. And Scala folks have reason to do that, because they have the magic tail rec annotation, which arguably improves performance. So they tried to show that in the benchmarks, right? So what they did this. They had the very synthetic test. They said, we'll try to do some basic arithmetics. And isDivisible method there actually checks whether the value v is divisible by all the divisors between starting d and limit L. So this is actually the tail recursive loop by d, right? And in your benchmarks, you try to find the first integer which is divisible in all the divisors from 2 to L. This is a very nice benchmark. GMH, there's the GMH annotation benchmark on it. We have the bindings for Scala, so it's kind of cool and fuzzy there. And it also enables us to have the direct rewrite to Java, which is this. Just one-to-one comparison there, right? But Java does not have any tail rec optimizations, right? We want to have them, but there's none yet. So our mental model is that Java should really lose big time on this benchmark, right? Who thinks Java loses on this benchmark? Who thinks Scala loses on this benchmark? Who thinks they are on par? All right. So the people who do this kind of benchmarks, the limit there is somewhat free variable there, so we want to juggle it as well to see whether we are measuring in some lucky condition for some lucky L. So we will juggle it as well. And this is the performance data for Scala bench and Java bench. This is the microseconds per op, so the lower the better. And Java benchmark wins big time, more than twofold increase over Scala test. What's up with that? How do we even approach this benchmark? Ideas? What to do when you measure stuff and you realize this is what's happening? What to do next? Yeah, most people, however, would profile first. And they will take some sort of off-the-shelf profiler which does the method-level profiling. And this is the profiler which is very naive. It's bundled with GMH. We just made it for fun. But all other method-based profiler will tell you the same picture. We have the two hot methods in profile, the test itself and isDivisible. isDivisible is hot. It's not inlined in test because it's recursive. Our hotspot is not really inlining recursive methods well for a reason. So this is it. For Scala, we just say, OK, tailrack actually inlined the thing there in test, so we have the only single hot method there. What do we get from this profile? I get nothing, and this is the lesson. Coarse-grained profilers, method-level profilers, are mostly useless for diagnosing these kinds of issues. They have additional penalty points if they sample in safe points. I think I have just 2 or 3 safe points in this code. So the profile is way, 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 way off. There are better strategies for doing this. When Jeremy has the get async trace-based profilers, and many people around the world are experimenting with this kind of stuff without doing safe points. And we also can do better. We need to go deeper there, right? We have print assembly. We can print the generated code. But the problem with print assembly is that it usually dumps at you tens of megabytes of assembly, and you have to figure out what's going on. Even if I know what method I'm looking for, there are different versions of this method in the code, and I have no slightest idea what method is actually executed. So we need to contrast these parts with some facilities there. Luckily, on Linux, we have perf, which can get us the addresses of the hottest instructions in the instruction stream. And print assembly has the addresses, so we can map the events from perf back to print assembly. JVM debug info has the mappings between the compiled methods and the addresses as well, so we can profile actually quite nicely. The code there is very, well, it's not very simple, but it's simple enough to play with it for fun. This is not a substitute for the big gun profilers. You will probably like to do some sorts of Solaris Studio analyzers kind of stuff if you want to get very serious. But when you're dealing with hundreds of benchmarks, when you need to analyze, these kinds of shortcuts really get handy to quickly diagnose the performance issues. So let's see what's there in Scala and Java. This is the hottest thing in Scala. This is the very tiny block of instruction stream. And it's in the method test, in synthetic GMH method, which really does the looping between invocations. And we see there the x86 division, honest x86 division. And it takes most of the time. It takes more than, well, the entire loop takes more than 95%. How can you possibly be 2 times faster than this? It's hardware, dummy. You can't really be faster than this, right? Let's see into Java. And in Java, we have isDivisible, which is not inlined. So it's like a lone warrior there trying to compute stuff. And we also see IDivs there. And they also contribute to a lot of CPU time. But this is not the only hottest thing in Java. This is the second hottest thing in Java. And if you look at the print assembly, you will look around IDivs, and you will find nothing. And you will see that this block of code, for some reason, references the IRAM bytecode instruction. So it looks like this is the integer reminder, but there is no IDiv. What's that? Yeah, that's just a beautiful trick. When you know your modulus, you can change your reminder or division operation into the multiplication and binary shift when you know this divisor. Right? And so this is why Java version is arguably faster. But why is it hotspot applied this optimization in Java benchmark, but did not apply it in Scala benchmark? Any ideas? This is the answer. This is the Java code. We do not inline isDivisible very much. We only inline it in the test once, and then we divide inline is divisible once in its body. This inlining provides us with the useful information that we know the divisor exactly. Because we know that the first call of is divisible is called with 2, and the second is called with 3. So we can specialize for divisors there. For Scala version, we are not as happy because tailrec already modified our code into the loop, and we don't peel the loop iterations from there. And so we do this generic IDIF on every single iterations there, and that costs us a lot. So these are these tiny little details that make your comparisons unfair. And it's arguably a benchmarking quirk because we only set up Java into the favorable position, like we are putting it into the aquarium and put the squid in it, right? And Scala, the cat, is drowning in the aquarium besides it, right? So we want to make inputs unpredictable. In GMH way, we just load this starting D from field, and by GMH contract, we will break the constant optimizations when we read the inputs from the heap. And if we do that, we will arrive to this performance data. And the Scala and Java benchmarks are roughly equivalent. Scala version is actually a little bit faster, and this is the true benefit of tailrec. We do not do recursive calls. In Java, we do recursive calls. In Scala, we don't do recursive calls. This is the true cost of tailrec. So benchmarks without this kind of analysis really make me a very sad panda. You can show me the nice charts. This is the language A versus language B, or this is Nashorn versus Rhino, or this is Graal versus C2. And all I see there, if I don't hear the explanations for these numbers, is some sort of noise. It's not the white noise. I mean, there is data in there. And these charts really mean something. It's just you don't know what actually that data means unless you actually dive into there and see why this particular implementation is faster in this particular case. Is it really burnt of some tiny detail like we did with Scala? Is that comparison really fair? And to conclude, it's really hard for us as the human beings. Not that. Hold that thought. When I invest 5 years of my life developing something and then running the benchmark against it, I'm conditioned to easily believe any benchmark which says that my product is actually superior. And vice versa. I would like to disregard any benchmark which says that I just wasted 5 years of my life. So when you do this kind of superficial conclusions from benchmarks, those conclusions are inevitably feed from your biases. And those biases are almost always wrong. So do the analysis to detach yourself from the biases you have about the results. Do follow up what those results really means. And the benchmarks are there to understand the reality, to understand how whatever complex thing it turns to be. It's just for understanding the reality, not for reinforcing our prejudice about the universe, about how beautifully performant the things that we just wasted 5 years developing right now. So if you're not analyzing your benchmark, you're going to waste a good time of your life. So please do. I would be happy to assist you in that. And on this, my talk is over. Thank you. Jeremy had a lot of questions. Right.
Oh, I guess there is one. Are you sort of training for an invariant timestamp counter that you use instead of data time?
Sorry, come again?
Well, you know, the way the cheap way to measure time is just to be a clock counter on the CPU. And truthfully, we need it. We have to go through this thing where we clock every time on a given
Yeah, yes. The problem is, yeah, there's the RDTC-P, which is monotonic across all the CPUs, and you can access it. And you can even write the intrinsics, and I try to make this experiment. But the latency figures are not really much better. So it still costs you in the ballpark of 10 nanoseconds. Yeah. So the cost of, well, it's no magic. You have CPUs which run their own clocks, right? You have to synchronize it in some way. So if your software doesn't do that, your hardware has to do that anyway. So this is the intrinsic cost of measuring time. Yeah. Reconsider the special theory of relativity. Yes. Intel, please do that for us. Okay.
Our biggest CPUs have a globally system synchronized RDTC, which is monotonic, and a cost.
Okay, cool. Yeah, so maybe in 10 years from now, we will have the decent benchmarking platform. Right now, we still have to measure performance. So take this in mind. Right, anything else? No? Thank you.